Hello, welcome back. We're going to solve the second problem on the ideal reheat power plant. This problem presents a challenge that we will need to iterate. So we have a steam power plant that operates on an ideal reheat Rankine cycle between the pressure limits of 15 megapascal and 10 kilopascal. The mass flow rate of steam through the cycle is 12 kilograms per second. Steam enters both stages of the turbine at 500 degrees. If the moisture content of the steam at the exit of the low-pressure turbine is not to exceed 10%, determine a. the pressure at which the reheating takes place, the total rate of heat input on the boiler, and the thermal efficiency of the cycle. Also show the cycle on a TS diagram with respect to saturation lines. So we'll start by drawing our TS diagram. We draw our saturation lines. These lines, remember, are 10 kilopascal. It should be a straight line. And 50 kilopascal. We have a pump that will do all this work for us. And we have a second extraction point which we don't know where it is. We only know that we need to find it. Let me just extend this line because we're gonna need temperature. So we have 500 degrees. Then we have this isentropic expansion until we get to this pressure that we don't know which is. And then we expand again until we get to 500 degrees. Then we expand it. Could be here or inside the dome. So we have our state 1, 2, 3, 4, 5, and 6. What does this represent in the real cycle? Is we have a boiler where we give heat, get this steam, and introduce it to a high pressure turbine where we are going to get work. Then we extract it, pass it through a boiler again, and then take it back to a bigger turbine because it expands at a lower pressure. So we have our first and second work from the turbine. Remember that these two turbines are connected through the same shaft. Then we take it out, pass it through the condenser, and in this condenser we reject heat, saturated, we pass it through pump. So now to identify each one of these, we have 1, 2, that was the pump. Just close these. 3, the inlet of the turbine. 4, the extraction for the low pressure. 5, inlet of the low pressure turbine, and then 6, the extraction. So we start as usual by defining what we were required to find: the efficiency, the extraction pressure, and the heat that we add. Let's start just by remembering that the efficiency is the net work divided by the total heat. In this case, the net work will be the work of the first turbine plus the work of the second turbine minus the work of the pump. All this divided by the QE, what we are going to find. Please take a look that we are not considering the heat rate or the power, we are considering just the specific work, since all of them are affected by this mass flow rate, and this will be constant. So if we elaborate a little bit, we know that these two works of the turbine will be the portion of the high pressure plus the portion of the low pressure turbine. Just let us say that this is high pressure, low pressure. And the work of the pump, it's H2 minus H1. That can be approximated as the specific volume at conditions of saturation minus the pressure difference. Finally, QE will be the summation of the first part, H3 minus H2, plus the reheat section, that will be H5 minus H4. So we call this the main, and this is the reheat. Okay, so notice that all that we need to do is to find out each of these properties, and we are going to do that just next. Okay, so let's define first state 1, and this is quality equal to 0. That means that it's liquid water, pressure equals to 10 kilopascal. Remember, we're making this assumption because we have an ideal reheat cycle. So if we go to our paper tables, we use table A5, the pressure table. Sorry, let me just move. And you can see that the 10 kilopascal have this pressure, this specific volume, and this enthalpy. So at table A5, we find H1 to be 191.81 kilojoules per kilogram, and B1 to be 0.001010. So we need to change this. Cubic meters per kilogram. State 2 is pretty straightforward. We know that H2 will be H1 plus work of the pump, and that the work of the pump can be approximated as V1. This we already know it. So we know it's V1, so it's 0.001010 times the pressure difference, and we know that pressure 2 is 15,000 kilopascal minus 10. So work of the pump doing the math will be 15.4. Let me do this a little bit better. Sorry, it's 15. Oh, it was correct. 15.14 kilojoules per kilogram. Stage 3. We know we have a pressure of 15,000 kilopascal and a temperature of 500, so that makes it superheated. Superheated vapor. If we go to table, so we have 15 megapascal and 500. So these are the properties that we're going to use, especially enthalpy and entropy. So if we go back here, we can use the data that we check. So it was H3 equals 3,310.8 kilojoules per kilogram, and S3 will be 6.3480 kilojoules per kilogram Kelvin. So now we are right to the first problem, because at stage 4 we don't know the pressure. We do know that entropy remains constant, and with that we will need to check S4 compared to Sg. That means the entropy at the saturated vapor entropy at pressure 4. We don't know which one it is, but this will help us to define if we have superheated, saturated, or a mixture. But we don't know. Once that we find out that, we get H4, which for the time being we don't know. Pretty much happens with the stage 5, because we know that P4 equals P5, which doesn't look like a lot of help since we don't know it, but we know that temperature 4 is Sorry, let me do this a little bit better. It's 500 degrees. So, since we don't know, we're gonna say that we're gonna find out H5 and S5 at P5 and 500 degrees. But we don't know right now. So we move to state 6 that we know. We know that we have pressure equals to 10 kilopascal and quality is 90%. Let me stop a little bit here. Why do we say that 90 is 80% if the statement says that we can get up to 90%? That means that is the maximum. We cannot have 80 to 83. We could have from 90% on. And we would like to have this because we know that the way of getting this, we go back one page, is by lowering this pressure, right? If we lower this pressure, then we increase the moisture content, but at the same time, if we lower this pressure, all this work will be increased. So we're going to choose that 90% because the reasons I have explained. So we know that we have okay, we go to table 5, A5 again, add 10 kilopascal, and this time we're going to look for these values in order to compute the quality. And since we already know the quality, sorry, we are going to compute just the value of A. So, looking at the table, okay, so H6 will be HF plus X HFG at 10 kilopascal, as we already said that. So this will be 191.81 plus 0.90 times 2,392.1. So this will be 2,344.70 kilojoules per kilogram. We need to compute also entropy because we know also that entropy 6 equals entropy 5. We don't know, but we're going to find it. So entropy 6 will be SF plus X SFG, and you can do the math. This result is 3.3988 kilojoules per kilogram Kelvin. So we know all the data that we can get. So how do we find out P5? Well, it turns out that we will need an iterative process, and this process will be just like this. So we need iterative process. Okay, so since S6 equal to S5, we can guess a value of P5. Okay, we know that at this S5 needs to be superheated. So we guess one value. Let's say that we guess 2 megapascal. This 2 megapascal will, if we decide that we have 2 megapascal, we go to our superheated vapor at 2 megapascal. Okay, here we are, and we notice that we need to be at 500, so that 500 pinpoints, and we know that S6 is equal to 7.3988 kilojoules per kilogram. So we know that at 2 megapascal and 500 is 7.43, which is about this number. At 1.8 kilopascal is 7.48, which is higher, so we need to go in the other direction. At 2.5 we have 7.32, so we know that we are in between these two, so we don't have to iterate, we need to interpolate. And this could be a good chance to remember how to interpolate. We're going to do it once. The rest of the interpolations you're going to do them yourselves. So we know that we interpolate using a similar triangle. We know that at 2 megapascal we have 7.3254. At 2.5 we have 7.4377, and that at P5 we're gonna get 7 point, let me fix this one, otherwise you cannot understand it. 7.3988. So this is a similar triangle, so this the ratio between this line and this line is the same as this line to this line, so we can write this expression P5 minus 2 divided by this length, which is 7.3988 minus 7.3254 equals 2.5 minus 2, that is all this line, divided by 7.4377 minus 3254. Solving for P2, we're gonna get that, sorry, this is not P2. Oh, sorry. So solving for P5, we get that P5 equals 2.34. Doing exactly the same with the same triangle, but instead of P's we get H5 is equal to 2860. Okay, sorry, wrong number. This number should be 3464.6. Now we have P6, we also have, we have P5, and we know that P4 is equal to P5, which is 2.34. So now we need to guess if this is a superheated or saturated or is a mixture. And in order to do that, we're going to need to do a double interpolation, because we know this is one value. The second value is that S4 equals S3, which we already computed as 6.3980 kilojoules per kilogram. So let's write here our interpolation pan. Each of these interpolations will follow the same scheme. Okay, we have at pressure equal to 2 megapascal, we have 6.3390, and to that it corresponds an enthalpy of 2877. We have a second enthalpy of 6.4160, correspond to an enthalpy of 2836.1, and we have our own enthalpy 6.3980, and we need to interpolate between these two numbers. And just to make sure that we stress that this is not value from the table, I'm going to change the color, and I know that this value by interpolation will be 2827. I'll put this by interpolation. We can see these values here, 2, these two values. Right? Okay, we're going to do the same as 250. So at pressure equals 2.5 megapascal, we do our same area. I'm going to do it to the left so we can interpolate in the middle. So we have 6.2629, which corresponds to an enthalpy of 2805.55. We have an enthalpy of 6.4107 that corresponds to an enthalpy of 2880.9, and again our S5, which is 6.3980, and again just by interpolation we're gonna get a value of 2874. Change colors again, because the pressure that we are looking for, thought that I was changing colors. The pressure that we are looking for is 2.34, right? This 2.34 is the number that we get from the interpolation on the pressure. So interpolating this value with this pressure, this value with this pressure to 2.34, we find out that H4 equals 2,874 kilojoules per kilograms, again by double interpolation. Okay, so finally what is missing is just put the numbers, these numbers, and H5 and H4 into these expressions. So you can do that, and just for your reference I'm going to give you the result that you should be getting. Okay, let's keep doing with green. We know that the efficiency should be 41.95%. These numbers could change a little bit depending on your interpolation. The total heat in will be 44.5 megawatts, which is Q in times 12 kilograms per second, and before we already computed is 2.34 megapascal. So with this we finish. Okay, and yes, thank you. Next video will be this problem but solved by ease. Okay, thanks very much.